Hi everyone. This is the review video for Physics 2 for Test 3. We will be going over three kinds of problems: Kirchhoff's rules, capacitors, and RC circuits. So let's begin. Let's begin with this circuit that we've got here. We know some things about the circuit. We know that there's current through this battery, 2 amps, up. We know that there's a 4-volt battery here with 1.5 amps down. And we know that the voltage drop across this resistor is 9 volts. Now I've got a lot of things to figure out. First of all, find the magnitude and direction of the current in this middle resistor, R4. So think about that for a second. What rule would you use to figure this out, to calculate this? All right, if you said the junction rule, then that's right. So we can look at either of these junctions, but they'll be the same. And so we'll just pick that one up there. And we will say that 2 amps, if 2 amps are going up here, then 2 amps are going around here. And if 1.5 amps are going down here, then 1.5 amps must be going across here. You have to have the same current going through here that goes through here because there's nowhere else for the current to enter or leave. And so going into there, we'd have those 2 amps. Going out from there, we'd have the 1.5 amps. And then, okay, anything going in is positive, anything leaving is negative. We don't actually know if the current in R4 is going up or down. So we can just say plus X until we figure that out, and then set the whole thing equal to 0. That's the junction rule. 2 minus 1.5 plus X is equal to 0. X must be equal to 0.5, and it must be a negative 0.5. 2 minus 1.5 minus another 0.5 does in fact equal 0. So if that's minus 0.5 right there, then what can that tell us about the direction of the current in R4? Think about that for a second. Yeah, anything that's negative is going out, and therefore the current through I4 is 0.5 amps down, going out from our specified junction. Okay, next part of this, next question. Find the voltage in battery 1. What rule will you use to figure this out? Okay, I hope you said loop rule, because that's what we need to do. Loop rule, we always start behind a battery. Doesn't have to be the largest battery. Here we don't know which is the largest battery, but we'll start back there just because. Now, you need to make a loop somewhere around this circuit. There's really 2 loops that you can make starting from there. You can make a small loop that goes around R4, but we don't know the resistance of R4. We don't know the voltage drop of R4. We do know the current, but we don't know the other things that we need. And so instead, we have to go around another loop, the complete outside loop. So starting from there, going up and around, we will pass over this resistor, this battery, and then return. So let's see what that looks like mathematically. We start at E1, so we write down E1. We go up and over. Now, I said that there's a 9 volt voltage drop there. But when you go across a resistor the correct way, the same direction as the current is flowing, you subtract. If you go the opposite direction, then you add for the resistor in this rule. But we know that the current is going down in that battery. And if it's going down in the battery, it must be going to the right in R3. So our loop is going the same direction as the current up there, and so we do in fact subtract the 9 volts. And then we go across that battery the correct way, and the rule for that is we have to add, and I should have said, the 9 volts here, we usually replace it with IR. Whenever we go across a resistor, we replace the resistor with IR. But we know I, 1.5 amps, but we don't know R for that. But we do know I times R. It is the voltage drop. V is equal to IR is the voltage drop, and we know the voltage drop is 9 volts because, well, I said so up there. And so therefore, we can say IR is equal to 9 volts. So that's where that 9 came from. It is IR, but IR is 9, even if we don't know exactly what I times R is. We could figure it out, obviously, but we're skipping past that, I suppose. Then, easy math, we figure out that E1 is equal to 5 volts. Okay, well, next part, find R3. We need to find that, and this is where we figure that out. V is equal to IR, 9 is equal to 1.5 times R is equal to 6 ohms. This is in part just to show you that you can find things a little bit out of order and it still works. And even if you only know a voltage drop, you don't necessarily have to find R in order to complete something like this, but you probably have enough information to figure it out anyway. Okay, let's look at capacitors. Here we have well, these are supposed to be a parallel plate capacitor, 2 parallel plates. They're 1.5 millimeters apart, total capacitance 30 nanofarads. Let's see what we need to do. We need to find the area of each plate. Well, think about our options for how we can do this. What equations do we have that would allow us to find the area of each plate? What about this? Capacitance is equal to epsilon naught times A over D. Well, we know capacitance, 30 nanofarads, 30 times 10 to the minus 9. Epsilon naught, we find that in the equation sheet. A is what we're looking for. Distance between the plates, 0.0015 meters, 1.5 millimeters. Remember those conversions. And we solve. Doesn't take too long for that one. Well, what if the electric field between the plates is 2,000 newtons per coulomb? Can we find Q from that? Think about what equation or equations we might need to use for this. Okay. What if we go back to our old favorite C is equal to Q over V? Well, that has Q in it, and it relates Q to C somehow, but we don't know V, unless we take this equation. V is equal to E times D. This is true if the electric field is constant, and it is constant in a parallel plate capacitor. So we can take this V, plug that in there. We need to calculate what that V is. So C is equal to Q over ED. C is 30 times 10 to the minus 9. Q is our unknown. E is 2,000 newtons per coulomb. D, the distance that you're traveling in that electric field to produce that voltage, 0.0015 meters. And then solve 9 times 10 to the minus 8 coulombs. What if we have an RC circuit? What if we put this circuit, this capacitor, in a circuit with a resistor? What's going to happen? Let's say that when we do this, the initial current in this circuit is 10 amps. Capacitor is still the 30 nanofarad capacitor. And at 4 seconds after we pull the switch in this RC circuit, our current has dropped from 10 amps to 5.866 amps. What is the value of the resistor? What is the resistance of the resistor in this circuit? How would we find this? Well, let's use this equation. The current as a function of time is equal to the original current times e to the negative t over RC. What is the current at the time that we're looking for? It's 5.866. What is the original current? It's 10 amps. What is the time? It's 4 seconds. What is R? It's what we're looking for. What is C? It's 30 nanofarads. Pretty easy after that, but let's just walk through the algebra just to make sure. We plug in 5.866 amps, we plug in 10 amps, we plug in 4 seconds, we don't know R, we plug in 30 times 10 to the minus 9 farads. We can divide both sides by 10. We have to do that, in fact. What we want to do is take the natural log of both sides, and while you can just take the natural log of 10 times e to the stuff, you don't want to. It's annoying. So what we do instead is we make sure that it's all numbers on one side and all exponential on the other side. So divide by 10. 0.5866 is equal to e to the negative t over RC. Then we take our natural log of both sides. The natural log of 0.5866 is negative 0.5334. The natural log of e to the negative 4 over r times 30 times 10 to the minus 9. Well, you just lose the natural log and the e, and you just make that normal. So that would be minus 4 times r times c. The minus there and the minus there canceled out, and I already made them plus there and there. That will often happen in this kind of problem. You'll have two minus signs that you need to cancel out. And then it's just a normal problem. Then you can just solve for R normally. 2.5 times 10 to the 8 ohms. For this test, something you need to think about is there's a lot of equations that you need to deal with, and there's a lot of methods that you have to think about. Method, I'm talking about Kirchhoff's rules. There's a lot of patterns in here. There's a lot of understanding how to set this kind of problem up, how to set up the equations. When you can use V is equal to IR, the answer is almost always if it's a resistor. If it's a resistor, you can use V is equal to IR. If it's a battery or a capacitor, you can't really. But you can use junction rules, you can use loop rules, you can use V is equal to IR. You may or may not have to find equivalent resistances on a mathematical kind of problem like this. It could also be conceptual. But there's a lot of methods involved here. Understanding how to set this up is going to get you 80% of the way there. And it'll probably get you at least half the right number of points just for setting it up. So remember that as you are working on this and studying for this. And of course, also remember all these capacitor things. When you can use C is equal to epsilon naught A over D, that's only for parallel plate. When you can use C is equal to Q over V, that's for all capacitors. You'd probably just need to figure out what Q is somehow and what V is somehow. There's a lot of different ways that we have to find Q and a lot of different ways that we have to find V. And so if you had a problem that involves C is equal to Q over V and you had to find C, well, I'll probably make you do something creative to figure out what Q and V are in order to find C, or some variation of that that you'll have to do to figure that out. And then RC circuits, just remember those equations and how to use them. They'll be on the formula sheet, of course, but know how to use those equations and how to actually solve using logarithms a problem like that.